Hello everyone. I'm Anmol, and I'm going to be the session host for the next 3 sessions. Hope you all are enjoying the conference. We just saw some really amazing lightning talks. Let's jump onto our next talk in the geo track. It is Gaps in the Grid, the Promises, Pitfalls, and Resurgence of Discrete Global Grids in Modern Geospatial Analysis by Max Gardner. Max is a PhD candidate in Civil Systems Engineering at UC Berkeley. Welcome, Max. The stage is all yours. You may please proceed.
Okay, thank you. Can everybody hear me all right?
Yeah, it's perfect.
Okay, great. So thanks for having me. I submitted this talk kind of on a whim, and it turned out to be a bit more, a bit larger in scope than I originally anticipated. So I'm going to try and kind of zoom through this as fast as possible, hopefully leaving a chance for to answer questions at the end. So let's now share my screen.
Perfect.
Okay. So the title, this is the title of the talk, Gaps in the Grid, the Promises, Pitfalls, Resurgence of Discrete Global Grids. So normally I would start with a show of hands oh, can everybody still see my screen?
Yeah, it's visible.
Okay. A show of hands of who knows what discrete global grids are, and who knows what the H3 Luber library is. But since we can't do that today, I kind of gave my best guess of what that might look like. From where I sit, H3 and discrete global grids have kind of become synonymous in recent years, especially in the Python world, where we don't really have so when I do this, can you guys see my notes?
No, only your browser is visible.
Okay, great.
Yep.
So from where I sit, primarily as a user of geospatial technology, discrete global grids have kind of become synonymous, as I said, with H3 in recent years, especially in Python world, where there aren't many good alternatives to H3. But I'm not gonna, rather than spending the next 20 minutes picking on H3, the goal of this talk is to kind of situate H3 within the historical trajectory of discrete global grids, to ask the question, what is it that discrete global grids actually do, so that we can help other users of the technology like myself answer the more useful question of, is it the right tool for me? So the goal of the talk then is to place these tools, discrete global grids, in a historical context in order to highlight what they do well and where they fail. In other words, what needs do they meet, and what needs do they not meet, and what Python-based DGGs, what could they do better than they currently do? This is the overview. We'll skip through that. Starting with the basics, what is a discrete global grid? A discrete global grid is a mosaic or tessellation which covers the entire Earth's surface, and it's comprised of basically what are grid cells, which are defined by points, and then the regions. The points or regions may either be explicitly defined or inferred. So if only the points are defined, you could infer the regions from a Voronoi geometry algorithm. If only the regions are defined, you could infer the points from the centroids. What are they used for? Primarily, we're familiar with discrete global grids and used for spatial indexing, because neighbor relationships and neighbor-to-neighbor distances are well defined in discrete global grids. They make excellent systems for storing and retrieving geospatial data, and the quad tree is an example of that. We also use them for data visualization, because in particular, a big reason why they're used for data visualization is that they claim to make it possible to ignore map projections, which is a claim that we'll come back to later in the talk, but I wanted to mention here too. They also overcome many of the visual biases that are associated with traditional geospatial visualization techniques that result from either irregularly defined administrative boundaries or the choice of the projection system, which can result in spatial distortion, especially when you're looking at the global scale. And the last thing they're used for is spatial analysis, which we'll also be coming back to. So to provide a little bit of context, we're going to start with a geodetic perspective and then talk about the history. So from the geodesic perspective, you can think of discrete global grids as a combination of a coordinate reference system with well-defined and indexed partitions of that, using that coordinate reference system. And I won't go, just for the sake of time, I'm going to kind of move fast through here. As best I could tell, the earliest example of a discrete global grid is actually the universal transverse Mercator system, which divided the Earth in 60 strips and then numbered them. And so it's really this indexing of the projection that defines a discrete global grid. In the 50s, we had a paper from Bailey who described what he called area reference grids. He was starting from the perspective of the latitude-longitude-based graticule, which does not preserve equal area regions if you were to use lat-long to divide the surface of the Earth. And he proposed a few solutions based on transforming either meridians or transforming the parallels of the lat-long graticule in order to achieve that desired effect. In Kurihara in the 60s, he took this a step further. Rather than defining regions, he defined his DGG based on points on the sphere in order to assist with climatological modeling. In 1975, everybody's favorite geographer, Buckminster Fuller, proposed the geodesic dome, which is basically, again, another way of partitioning a sphere into well-defined equal area geometries. 1985, Tobler and Chen presented the global quad tree, which was actually the first paper I found that I thought was really unique because of this quote here: "The traditional map functions both as a data storage device and a geographic display, and these two uses can now, in 1984, now we can separate them," which is really interesting thinking about what we're wanting to do with DGGs today. One, we use them as a spatial index, that data storage device, and then also as a geographic display, i.e. data visualization. 1994, Michael Goodchild, Santa Barbara, he wrote a paper where I think was the first to actually use the term global grids. He presented a set of criterion for evaluating them as well. And then in 1999, Kimmerling, Saar, and others actually used those criteria to evaluate how can we identify the best discrete global grids for a given use case. And it was Saar who's kind of taken this trajectory to its logical conclusion. He established the Discrete Global Grids project in 2003. And he's kind of, we'll see more what his work has led to later. So in more recent history, a great example of another use case for discrete global grids is the geohash algorithm, which I'm sure many of you are familiar with. In 2011, Google actually released a kind of quietly a great discrete global grid called S2, which was primarily used for spatial indexing. They have a rectangular hierarchical discrete global grid that allows for fast retrieval of geospatial information. 2013, another interesting, unique example of what discrete global grids can do is What3Words, which basically divided the entire surface of the Earth into these I believe 3 meter by 3 meter cells and index them by these English words, sets of 3 English words. And then 2018, the new kid on the block, the kind of inspiration for this whole talk is Uber released H3. And we'll talk more about that later. So with this context now, I want to kind of reframe the discussion in terms of what specific problems I think folks like myself who spend more time using Python for data analysis than for software development, what might people like me want to actually use these tools to solve. So spatial indexing, that's a big one. We already discussed. The ability to ignore projections. In my opinion, this is probably the #1 driving factor in the popularity of discrete global grids, particularly as computer scientists and software developers have, taken a driver's seat in terms of pushing GIS forward as a field. These folks are probably less familiar with map projections, more familiar with spatial indexing, and therefore, anything that allows them to ignore map projections, which to some degree I think is a reasonable response, they're all for it. And then lastly, we want to be able to use arbitrary equal area units of geography to perform spatial statistics, because having equal area units is really a prerequisite for doing solid spatial statistics for a few reasons. First, the fact that they're arbitrary means that on a local scale, they're unbiased with regard to endogenous spatial patterns, demographics. So they're exogenously defined, meaning we don't have to worry, about, we can completely separate the geography, the unit of geography, from whatever data we're seeking to analyze. And then on a global scale, we want to be able to use consistently defined boundaries. So if you're in the United States, we have zip codes, we have census blocks, we have census tracts, we have counties, all these things that geographers, demographers, social scientists, people use to analyze data. But if you want to compare that to a different country, we don't have a good way of doing that. And discrete global grids allow us, give us that ability. The other thing that we want to do with discrete global grids is we want to be able to look at our data on a globe without the spatial distortion, or rather than view it on the globe, we want to be able to define these equal area units based on, without suffering the same spatial distortion that we would incur if we were reliant on that latitude longitude based graticule, which is, that's the problem that so many of these folks I talked about in the history of discrete global grids were trying to solve. And then lastly, we want to be able to use discrete global grids to solve what's called the modifiable areal unit problem. So this is kind of tangential to discrete global grids, but it's important because I think that the ideas get conflated a bit. And more importantly, modifiable area unit problem rarely gets the attention it deserves outside of academic geography or urban planning communities. So I thought it would be useful to talk about it for a second to see what it is and how it applies to discrete global grids. So the modifiable areal unit problem in spatial analysis really means that the results of your analysis might depend on the geographic unit that you're using to measure your data. And this occurs on two scales, in two facets. One, the scale of your unit might affect the outcome of your analysis. And two, how you're actually defining the unit might affect the results of your analysis. So here's a great example that makes it really easy how these two facets can affect your analysis. So in the top row here, we see how the choice of scale of the unit can result in variable outcomes of your analysis. So on the top row, we're just changing the scale of aggregation, essentially, the number of pixels or units or boxes that were being aggregated, which can lead to vastly different interpretations of the data. On the bottom row, we see bias or variability that might be due to how the units are defined, rather than any particular aggregation scheme. So you can imagine, I'm coming from the United States. From the United States perspective, you might see very different results of your data depending on whether you're aggregating them from the census block or the zip code, et cetera. For those of you who follow American politics, this has been a hot topic for many years, based on how we view the distribution of Republican and Democratic voting on the United States map, is a good example of that issue. And discrete global grids portend at least to solve some of this by exogenously defining the geometries. Okay, so moving on to a use case. So I am in the civil engineering department at Berkeley. I work a lot with traffic data, urban mobility data, and this talk really grew out of my own work trying to incorporate H3 into a workflow of traffic equity analysis. So when I talk about traffic equity analysis, I mean, how are different segments of society, different demographic segments of society affected by traffic congestion or commuting distances, or how would a new bus line affect the travel times for different demographics in a city? These are the kinds of problems that we are concerned with. So I'm going to start this use case with just a bit of a deeper dive into the H3 library and what it's about. So, So H3 is actually very similar, it turns out, to Google's S2 library, but it uses hexagons instead of squares. So that means so it's like S2. It's a hierarchical DGG, but it uses hexagons. And I say mostly because if you actually look close enough, and I don't know if those of you out there can actually see my cursor, but if you look closely, there are pentagons embedded in the surface partition, which is done by necessity if you want to completely and consistently cover a sphere with geometric shapes. And the way that H3 does this is by combining the spherical icosahedron, which is this 20-sided geometric solid, with 20 different what are called mnemonic projections. So they've divided the sphere into 20 planes, and then they for each of those 20 planes they use a separate projection. So already, we're seeing that, okay, so discrete global grids, they give away, they're supposed to, I guess in theory, do away with the need for projections, and yet embedded in any discrete global grid, there is a projection. It's just a single well-defined projection that everybody who wants to use that grid agrees to use. And so the spherical icosahedron and combination with economic projection, it results in a kind of partitioning of the globe that looks something like this. This is all from Uber's H3's documentation. And although they were the first to implement it in this particular way, they didn't come up with the idea themselves. They were heavily inspired by Saar and a 2003 paper he wrote. I mentioned him before as the kind of progenitor of the discrete global grid project. This image, which looks very similar to what Uber has done, comes from Saar's 2003 paper. He kind of was the first to propose the combination of the icosahedron, spherical geometry with a sub-partitioning of mnemonic projections. But H3 wasn't even the first to come along and turn SAR's ideas into software. SAR himself released the DG Grid software shortly after he published that paper. There's actually a really excellent R library, sorry for mentioning R here, called DG Grid that does a very similar thing to what H3 does. But in any event, that's sort of what H3 is. So what does H3 do well? So the best thing about H3 from one perspective is their use of hexagons. So why are hexagons all the rage now in partitioning and data visualization and spatial indexing, all that? So for one, hexagons have the least average sampling and quantization error for both the covering problem and the packing problem. In short, the short version of that is that if we have, say, a national border or a coastline, and we want to use hexagons to geometrically approximate the shape of that, hexagon's going to do a much better job of approximating that shape than, say, triangles or squares. The other great thing about hexagons, which is shown here in the bottom row of this slide, is that neighboring cells have equidistant centroids. And this is particularly useful for the case of spatial indexing, because it means we don't really have to worry about neighbor to neighbor distances. There's one neighbor to neighbor distance for the entire index. We just need to count the number of neighbors to go between, and you know the distance between them. And so I think that's probably why Uber settled on the hexagons, because they are a mobility company and they care about distances and travel times and things like that. And storing their data using hexagons makes it super easy and super fast to store and then retrieve that data. The other thing that H3 is good for in terms of traffic is that it might be in some use cases better than the existing standard for analyzing traffic data, which is the TAZ, or traffic analysis zone. So for those of you who are unfamiliar with TAZs, and this is a TAZ map from Austin, Texas, and TAZs they are administrative boundaries. They actually used to be stored and standardized in the census as census tiger boundaries, but no longer are. So they're kind of being phased out, and I think that's part of this trajectory that I'm describing, is this case where TAZs are being phased out, and these DGGs to some degree are starting to fill that void. But in any event, TAZs are actually aggregations typically from census block geometries. So here we have the TAZ map of Austin. Zooming in, this is what it looks like with downtown Austin in the bottom right corner. And then underlying that are these are the census block geometries. The aggregation scheme is designed to make it such that each TAZ has a comparable number of trips arriving and departing from that traffic analysis zone. So rather than normalizing by population like a census block or census tract might try to do, TAZs are tried to normalize by the traffic generated by them. But what's tricky about these is that since they're not standardized, they are arbitrary. Each metropolitan area is responsible for producing its own traffic analysis zones. There's not one go-to destination for accessing this data. So if you want to do an analysis or run a simulation in a new region, you have to kind of spend a lot of time and energy just tracking these data sets down. So, discrete global grids make that much easier. And because they're exogenously defined, because they're consistently defined, it might actually mean that we have less modifiable areal unit problem because of these very things. But part of the point of this talk is to question the extent to which that's true.
Last 3 minutes left.
Okay, so I'm going to zoom through here. What's less good about H3 for traffic is that as far as hierarchical grids go, this is an unaligned hierarchical grid, meaning that the vertices of the hierarchies are not actually aligned. And this produces some pretty undesirable consequences. In particular, it makes it very difficult to traverse the hierarchy from low resolution hexagons to higher resolution hexagons, or vice versa, because a point contained in a parent hexagon may not be contained in any of the children of that hexagon, and vice versa. So for example, in this image here, these points, the green point clearly belongs to the parent hexagon in the top left corner. But if we wanted to traverse the hierarchy, we would eventually miss that. We would eventually run out of children of that hexagon. I know I'm not rushing here a little bit, but the other thing is that it forces us to make another byproduct of these unaligned hierarchies, and it forces us to make arbitrary decisions. So for example, if we have point geometries, we have to decide which hexagons we want to assign a point like the magenta point that doesn't actually fall into isn't actually contained by any of these geometries, whereas the turquoise is contained by multiple geometries. So how do we assign them? And then lastly, for demographic data is stored at the block geometry, and traffic analysis zones already exist as very nicely well-defined ways of aggregating that demographic data. With TAZs, we're forced to make arbitrary decisions about how we allocate those blocks to these hexagons, which results in some beautiful images like what I'm showing here, but it actually winds up undoing any of the benefits that we're hoping to obtain from them in a scenario like this, because it winds up being just as arbitrary as the original geometries defined by the census, for example. So in conclusion, DGGs, they let software developers ignore map projections, kind of, because behind every DGG, there is a map projection. They're great for spatial indexing big geo data, and the optimal cell geometry is a hexagon. However, they are not a solution for the modifiable areal unit problem in whole. And to that end, I'm making a call that Python still needs a good aligned hierarchical discrete global grid system, because H3 because of their use of hexagons, it doesn't do that for us. And so if any of you out there are interested in helping me lead this charge, do some work to make this happen, please reach out. Sorry I had to rush through a lot of these slides, but please, please don't hesitate to reach out to me. I'd love to talk about this more with anybody.
Thanks, Max. It was really an amazing talk. I hope that people found it useful.
Me
so
too.
We don't see any questions in the Q&A section. People, if you have questions, just jump onto GeoTrack. Oh, I see one. So the question is from Philip. He says, do you know of agencies moving towards hex grid?
I do. I would hesitate to name them here out of respect for those agencies. I think in terms of traffic analysis, a lot of agencies are subject to the whims of the software developers, because the agencies don't have the developers themselves. And so there are definitely software developers for many of the reasons I mentioned in this talk, are moving towards the hex grids. And as a result, so are the cities. That's part of the point of giving this talk is I think I'm someone who kind of bridges the gap between the two universes. I'm both a practitioner and a developer. I have done work for cities, and I've also done work for software developer, the people building the software. And so I think it's really important that for folks that do bridge that gap, that we are conscientious of our decision-making process and not just going with the flow because Uber is a sexy company, they write nice software. It is an open source project, and I don't mean to, I'm not trashing them in any way because it does a lot of great things. But because there's such a megalithic, because they have so much cloud and so much power in the software space, people tend to kind of go with the flow on that. And so I think it's just important to point out where it works well and where it doesn't. And that was the goal of this talk. Hopefully it came across.
Right. Thanks a lot for answering that question. I suppose that your question was answered, Philip. People, if you have any questions, just jump onto the Geo track in Discord and you may ask your questions there. Thanks a lot, Max.
Okay,
Yeah.
Thanks for having me.